So yeah, hey everyone, my name's Emma. I'm very excited to talk to you a little bit about strings in Rust. Um, Caroline's already mentioned, used to be a doctor, picked up coding, realized that I really didn't want to be a doctor in terms of a clinical doctor, and I wanted to switch to software engineering. Managed to very luckily get a job at a digital bank in financial tech, which I started about 6 weeks ago. It's mainly in C#.net, so that's completely new language and framework for me. So been a bit frazzled the last 6 weeks trying to learn it. But I was learning Rust before, and I'm still trying to keep up with sort of like open source stuff and keeping up with my learning now. So in terms of the outline, things I like to cover. So Unicode and UTF-8 and how it relates to Rust. Bit about the two most common string types, string and ampersand stir, which is what I'm going to call it. I'm pretty sure different people pronounce it different ways, but and then I'm going to go through the memory representation, a bit about string slicing, ownership and cloning. And then what I wanted to do was really emphasize the advantages of how strings are represented in Rust to try and convince you why it's so complicated or feels so complicated that it has a lot of advantages. I've also got a few slides on deref coercion that I don't think we'll have time to cover, but if you're interested, I can send you the slides or go over them. So what is a string? So basically it's just a collection, which is really just like a data structure which holds multiple values. It involves encoding characters to represent text, and in Rust, the encoding system that is used is UTF-8. Really, it's just like a sequence of bytes under the hood. So it's a sequence of bytes that the computer then interprets as characters. So thought I'd just give a few examples of the two most common types being used in case you haven't seen it before. So the first example is just declaring an ampersand stir in a string. Second example is an example of string concatenation, which you might have seen in pretty much all programming languages. And then the third example is an example of a mutable string. So you're pushing world to hello to create hello world. So what is Unicode? So you might have heard of Unicode being mentioned when it comes to strings. So it's basically a character encoding standard. What this means, it's sort of like a classification system for characters. So if you think about like species of animals or like diseases, they all have classification systems associated with them. So this is just sort of the same thing for characters. So each character will be assigned a code point, which is like a classification number, and it just identifies each one as being different. So how this links to UTF-8. So UTF-8 is the actual encoding system. So it takes the Unicode characters through some complex algorithm. It turns them into byte sequences of 1 to 4 bytes. You might have heard of ASCII, so it's another encoding system that's a bit more simple. I think it only encodes 128 characters, all of which are English characters. So the advantage of UTF-8 is it can encode non-English characters, such as like Mandarin characters or characters with accents and that sort of thing. So it's interesting because it's backwards compatible with ASCII. So the first 128 characters in UTF-8 are the same as the ones in ASCII, and they're encoded with 1 byte per character. But subsequent characters that aren't in ASCII are encoded using multiple bytes. I emphasize this for a certain reason, which I'll come to later because it's important when considering string slicing in Rust. But two of the major advantages of this is Rust can store more characters than if you were to use ASCII. And UTF-8 in particular is quite memory efficient because you're only using additional bytes, so additional memory, when you have non-ASCII characters. So other encoding systems use additional bytes when they don't really need to. So it's really emphasizing memory efficiency. So this is just a sort of simple table showing different characters. So the first two, A and B, are actually present in ASCII and UTF-8. And you can see that the decimal values of both of them are the same. But in UTF-8, it's encoding using 8 bits, which is 1 byte. But in ASCII, it's 7 bits. Then the subsequent 2 characters, the E with the accent and the Mandarin character, are not present in ASCII. So they're present in UTF-8, but they're encoded using multiple bytes. So just again to emphasize, 1 byte does not necessarily represent 1 character in Rust because it uses UTF-8. Okay, So, bit of a tangent, but I thought I'd just give an overview of memory, especially particular bits of memory, because it becomes relevant when understanding different string types. So, this is taken from a computer systems book. I don't have a background in computer science, but I've been trying to learn a little bit to improve my understanding of Rust. I think it really helps because Rust is a computer systems language. So the main things I want you to focus on is the stack, which you might have heard of before. You might have heard it uses last in, first out. It's for storing sort of fixed size, smaller variables, function arguments that are known size at compile time. In contrast, the heap is for values, for data values that do not have a known size at compile time, and the memory can be sort of dynamically allocated, deallocated to change the size of the data structures within it as your program executes. Then lastly, the last one I want you to look at is the read-only code and data. So this is where, so during compilation, it forms your binary code, which is basically the instructions for your program to run. So that is stored there, as well as some sort of variables that are embedded in that binary in the read-only memory. So those are the three I just want you to focus on and sort of remember, because now I'll go through the different types, and I've made some diagrams which hopefully will make sense. So this is a string. You can see actually it's made up of two different parts. If we focus on the part on the right, this is sort of the string data itself. It's just a sequence of bytes that's stored on the heap. So as I said before, the heap is for data structures that are not known at compile time. Memory can be allocated, deallocated dynamically, and the size can sort of grow and shrink as your program runs. So a string can be mutable. So it can be immutable or mutable depending on whether you declare it as such. As well as the actual string on the heap, you've got the actual string struct on the stack. That is a fixed size, which is why it's on the stack. And what it consists of is a pointer to that data on the heap, the length of whatever data it's pointing to, and the capacity of whatever data it's pointing to. So that is sort of how much memory has been allocated, which might not necessarily be the same as the length. So just to illustrate this using code to prove to you that this actually exists. So first line, I'm just declaring a string called hello. And the second line shows that you can actually print the stack memory address of where the string struct is stored. So that is the thing on the left in the diagram here. Then below that on the third line, you can see that you can also print the heap address where the actual string data is stored. So that's the thing. Sorry, that's the thing on the right. And the output is just in the screenshot below, so you can see those two memory addresses are different, showing that they're two different things, but they both sort of make up the idea of a string. So I thought I'd just mention this. So ampersand string. I mention it because I was very confused about this when I first looked at strings, because you often see ampersand stir used, but obviously there should be an ampersand string, and it was just all a bit confusing. So I just thought I'd make this diagram to show that if you see ampersand string, it's literally just a pointer to that string structure, which, as I showed itself, the string structure itself has within it a struct with a pointer to the data on the heap. Now, if you read about deref coercion, you will understand why this isn't really used, because ampersand string can be automatically converted to ampersand stir, which is a lot more simple. But I just thought I won't go through that now, but I just thought I'd mention in case you come across it. So moving on to string literals, which is what this is. So this isn't, I've mentioned ampersand stir, but this is a string literal, so it's a different thing. And I mentioned the read-only memory. So string literals are sort of embedded in the binary during compilation. They don't have a fixed size because it depends on whatever the word is. So if the word is hello or hi, they're going to have different sizes. And that's why it's sort of embedded in that read-only section. It can't change during runtime. So ampersand stir is slightly different, and hopefully I can sort of explain the difference between the two and why you're only really going to see ampersand stir in code. So on the left, I've declared a string called hey, and on the second line, I have declared a hey1, which is assigned to hey. So that hey in line 2 is actually a string literal. So you might wonder, okay, why is it declared as an ampersand stir and not a string literal? And it's because in Rust, during compilation, the compiler needs to know the exact sizes of the types. And because string literal is an unsized type, it can't possibly know what the size is going to be. So basically, whenever you have a string literal, it will always be behind an ampersand stir, behind a reference. So you can see that at the top on the top part of the left of the right-hand diagram. So you can see that you've got this pointer, hey1, and it's pointing to the read-only memory with the string literal in it. So to confuse things further, what I could do is say, got a variable hey2. I can take a string slice of the original string hey above to create an ampersand stir, and basically what that creates is a ampersand stir, which consists of a pointer and the length that points to the data on the heap. So basically what this is showing is the ampersand stir is basically, it just points to some sort of string data. It can be in the read-only memory, it can be on the heap, but it's just something that's pointing there, and it doesn't just have a pointer, it has the length as well. So it's all a bit confusing, but hopefully that makes a bit of sense. The good thing about this is with a string, you've got mutability, but with this, it allows for just read-only access because it's always immutable. So there's no risk of sort of changing things when you don't want to. So one other thing I wanted to mention, Rust strings don't contain null characters, like some programming languages, like classically C. So this prevents something called null pointer dereferencing errors. So say if you had a pointer pointing to something that was turned to null, which could happen if you have these null characters. If you then try to dereference it, it would just be sort of undefined behavior and your program might crash. So moving on just to string slicing. So the first example, I've declared a word, which I think is hello in Mandarin, with 2 Mandarin characters. And I have basically the second line is trying to access, what it's trying to do is access the second character onwards and store that in another variable. But you might remember I said these Mandarin characters are non-ASCII, so they're going to be encoded using more than 1 byte. So actually what this is doing is it's trying to access the second byte, but that's going to split this character. It's going to try and slice into this first character, which is not what you want. So actually Rust doesn't allow this and you'll get this error. Example 2, so this is actually all ASCII characters. So actually all of these are encoded by 1 byte. So you'd think this would probably work because the second byte is going to correspond to E. So you're just going to get ELO. But actually Rust doesn't allow this either. So it doesn't allow string slicing in this way, basically. And this is to prevent invalid access to strings. So it's better to interact with strings in this way by using sort of the docchars method or the docbytes method, depending on what you're doing. Okay, so just a little bit about ownership. It's a big topic, but I just wanted to give an example. So this is relating to strings. So say if I declared a string hi, I bound it to S1 variable, but then I took S2 and I then assigned that to S1. So what that actually does, so initially you have S1, it's pointing to this value on the heap, but then actually what happens is the ownership of this is moved to S2. So that now S2 is pointing to the heap and this gets dropped. So this is no longer valid and it gets sort of dropped from memory. You'll notice that during this, the heap value is not duplicated. And this is because strings don't implement the copy trait, unlike other sort of primitive variables like integers. And it's all managed using ownership, borrowing, moving, and that sort of thing. So what this does, it prevents multiple owners of the same data. So in Rust, you can only have 1 owner, sort of usually, of each data type, and it prevents stuff like double freeze. So say if these were both active and they both tried to free this memory at the same time, that wouldn't be very good. And say if these were both active, say if S1 caused this to be dropped, the data to be dropped, and then this one was still active and tried to access that memory, thinking it was still that data. It could be null, it could be something else could have been allocated there, so that's going to lead to sort of undefined behavior. But say if you did want to copy that data, so you wanted to duplicate that heap data, you could call clone. So when you do st1.clone, what it does, it will copy that data here, and it will the S2 will point to that. So basically, you have two copies. You'll hear some sort of articles or whatever saying to avoid using .clone because it's sort of uses more memory, I guess, because you're duplicating the value. But there are use cases for it. You just have to maybe just think about whether there's another way to do it or whether that's the best way. Okay, so this is like a summary table of everything I've talked about. As you can see, there's a lot to sort of consider, but I won't go. I think I've been through most of it, but I can sort of share it if it's useful. I just wanted to highlight the general advantages of ownership and borrowing in Rust, and especially with strings. So it has better performance compared to something like garbage collection. And this is really because it's enforced at compile time, whereas garbage collection sort of continuously runs during runtime, I believe. So it's more sort of efficient. It's also very memory safe because each value has one owner, and as I previously mentioned, prevents all these different problems. There's also no unnecessary duplication of string data. You need to intentionally clone something, which in other languages isn't the case. So you might have heard that actually there's like loads of different string types, lots of which I don't understand yet. You've got these weird sort of smart pointer things. So I haven't covered any of them. I just went for the two most common, but there is a lot more to it. So in terms of references, I use these three mainly. I think they're all really good resources. The first two are pretty good for like an intro to Rust. And this one is a bit heavier, and it's written assuming a sort of basic understanding of C, but it really helped me understand things like byte representation, the memory layout, and things like that. So yeah, this is the outline that I tried to cover. Just to remind you, I hope it was somewhat helpful. But I do think it's one of those things where everyone explains it differently, everyone learns differently. So however I explained it might not have stuck today, but there's a lot of different resources and different ways of explaining things. So just have a look around. Cool, and that's it.
Great. Let's all give a big cheer. Yeah, well done. This is your first talk on Rust, I believe, as well?
Yeah.
So congratulations, that was great. You've never said it was your first talk, so amazing. We've got a question already. Lisa, do you want to step in?
Hi, thanks really loads for that talk, because that's exactly the sort of thing that I don't understand about Rust. I'm just kind of using string, not really having any idea of the kind of memory and what it actually means underneath. So yeah, brilliant. What I was always wondering is, if you want to pass a string to a function, what type of string is best to pass? Because sometimes I get errors about lifetimes, and otherwise I have to do cloning, and I don't really know which is the best type.
I guess there's a few things you should consider. Like, so when you pass it to a function, you might be transferring ownership if you're using sort of a string. I think, Caroline, you might answer this question better.
I think it really depends on the use case. So I think in general, I would say don't pass the string in because of the issue with ownership. But sometimes you need to, or it's just more efficient to do it because, so like I had an example yesterday where I was writing a function, which then within it called another function, and that function only took in a string. And so you might end up with some like scenario where you might need to think about I don't really want to clone this, or whatever, or do some sort of conversion. So I think it depends on what your use case is, and also perhaps what the style, especially if you're working on a code base with other people, what they do. But I would say, in broadly, I'm sure lots of people on the internet are probably losing their mind right now, but I think depends on like what your use case is. But I would say broadly, like, try to borrow, like, you don't want to transfer ownership, so that should be your default, in my opinion. Does anyone else have any other opinions on that?
Well,
All right.
yeah. Unless you explicitly wrote a function that would change that string, then you may or may not want to either clone that value or indeed pass the ownership and then pass it back, because functions could do that. I guess that's one use case where you might want to actually, give it.
It's like a default. The default behavior, I would say, is don't do that unless you have a specific use case, like you want to do something on that string, or you need it to be a string for some other reason.
And I want to add something else. I suppose also when you're looking performance, because if you don't want allocations or cloning, right? So you might just use the ampersand. I just call it str, but I like stir.
Yeah, I think the Americans say like stir. So
Stir.
I didn't know whether I was
Stir.
weighing up what I say, but I thought I sounded less silly saying stir, but maybe I should have said str. I don't know. So
I go back and forth between which one to say. Okay.
Thanks.
So we've got a question in the chat. So could you touch on the differences between a string and ampersand string?
Sure.
I'll just go back your slides. Yeah.
Okay. So string, you've got the pointer length capacity on the stack, and it's pointing to the data on the heap, which is the actual string data. And this I just wanted to mention because it confused me when I saw it. It's basically just a pointer to that string structure. So this string structure here is literally just pointing as a reference to that string structure, which that string structure itself has a pointer that points to the heap. The reason you don't see it, and I can skip to maybe this, is because in Rust, it sort of implicitly converts that ampersand string to an ampersand stir, so a bit like this. So I think if you read a little bit more about that, it might make more sense. But yeah, it's basically just a pointer to the string.
Great, thank you. Any more questions? Oh, Yuza, take it away.
Yeah, I was curious what you built with Rust, sort of in between Code First Girls or during maybe Code First Girls and your first job now.
Yeah, so basically, I was working as a doctor. I was trying to learn to code, and I was trying to expand my community of people, sort of who'd switched from being a doctor to coding. And I just happened to sort of come across Caroline and also a guy called Max Flitten, and they both love Rust. And so they convinced me that Rust is pretty cool. And for me, it was a way of like learning, because I don't have a computer science background, it was a way of also learning some systems level concepts that I thought would be helpful, because it's a very systems heavy language. So I think I started just learning using sort of like resources, a few courses and things. And then Max and Caroline had some sort of open source projects that were sort of floating around. And I was like, okay, I'll give it a go, just contributing to those. So the main one I'm doing with Caroline, or helping Caroline with now, is relating to sort of epidemiology and code lists and managing those. So right now we're just sort of coding the logic, but hopefully it will be sort of like a desktop app sort of thing, full stack. So yeah, I'm just doing little bits and pieces with open source, but possibly in the future I'm not sure I want to stick with C#.NET, I think, and I think it'd be cool to do something more sort of in my work in Rust, but need to get some experience first, I think.
Yeah,
really cool.
Great advertisement for the open source
Yeah,
technology
it's
project.
fun.
We need more people. If you would like to come and do a Rust project, please get in touch with me. And there's lots of things to do, and it's a great way to get your code reviewed by someone who's working in Rust and just sort of collaborate on a project which is really needed. So I can talk about that if people are interested. Any other questions?
I'll just pop the email there, Caroline, and probably the best one if anyone wants to just get in touch with you.
Yeah.
And then you can email out. My question is building on just before Tim's comes in, Emma, how you got into it. And Ned and I were just saying, oh, this is a stretch session for us. I don't know about any of the other newbies. I recognize quite a few of the words, but a lot for it. Like, how long did it take you to get to this point of understanding and being able to do a talk on this? How many years? How much studying?
I mean, I only started coding last March.
No,
So
you're disgusting. No.
I just love it. Like, I just became obsessed, and I think I found it really, really interesting, and it sort of made sense to me. So I really had a goal of learning, being able to actually write proper code in Rust and contribute to projects. So I just used all the resources I could. Sort of alongside being a doctor, and then I did actually take 4 months off between finishing being a doctor and starting my job. I was doing the boot camp as well, but I had the days free, so I was just learning during that time as well. So
yeah. No, that's astounding. That is utterly astounding. And I think when it becomes that kind of compulsion as well, it's so exciting. It's all this kind of logic building out your brain. Did you find any bits at the beginning that were really helpful to kickstart that? You said about the open source project, so that was a really helpful way in.
Yeah, I think it is, because I think with Rust, it's important to have maybe sort of a vague understanding of the concepts. Maybe go through, I don't know, the Rust book, or there's a course on Rust Rover, a shorter one, but you can't really understand how to use it without just trying to write something, breaking something, seeing the error messages, and having someone lovely like Caroline who will look at your PRs and take the time to sort of comment and things like that. And reviewing PRs yourself as well is helpful to learn. So you also, if you're working on open source, you're doing it with other people, you don't feel like you're on your own, and it feels like I'm learning Rust for a reason, and I'm actually outputting something. So I'd say I would get into that as soon as possible, but obviously it's important to understand the underlying concepts, or have a vague understanding. And for me as well, I tried a bit to learn a bit about computer systems, just because it made it a lot easier when understanding things like the heap and the stack. Just gave me more of a deeper understanding of strings and why are they that way, why things are the way they are. Because Rust, I think the rationale behind Rust, some people say, is it's trying to improve upon sort of previous systems level languages. So if you understand why they were made that way, you can then understand what improvements have been made in Rust, and it just deepens your understanding a bit more. But I am by no means an expert. I did a tiny bit of C. I still want to learn way more, but that's what I tried to do.
It's very inspiring.
It is indeed. Okay, we've got one more question. Does clone create a copy on the heap as well?
Yeah, hold on. Just go back. Yeah, so it does. So that's the sort of point of cloning.
Emma, you'll just need to reshare. Sorry.
Oh, sorry. You see that? Yeah. So you can see when you clone, it creates this extra copy, and you've basically got two independent sort of pointers here pointing to separate copies on the heap. Whereas if you're just transferring ownership, there is no copying. And as I said, this is because strings don't implement the copy trait. And instead they are managed by sort of transferring ownership and dropping the variable that no longer owns the value. that makes sense.
So is that the reason why cloning is considered to be expensive?
Yeah, exactly, because you're basically using double the amount of memory on the heap. But like, if you think about it, is it that much of a big deal? I don't know. I don't know what metrics you can do. I think Rust engineers tend to be quite pedantic. So doing like one clone probably isn't going to make a massive difference. But because I guess in other languages, you might not have this advantage of reducing your memory usage. So you may as well take advantage of it if, just don't use it if you don't need to, just make a conscious choice to use it. Because it might be that you don't need 2 copies depending on what you're doing.
Yeah. Perfect. Okay. Any other questions before we turn the recording off? No. Well, please everyone join me in applauding Emma and her wonderful presentation, and also amazing career change. So very inspiring for everybody here. So well done.